Thank you. It is my absolute pleasure to be here, and it is my absolute pleasure to welcome you to Multiplai. So in case you haven't noticed, AI is having a bit of a moment with the release of ChatGPT and other generative AI tools in last fall. For the first time, really ever, AI was put right into the hands of the general public. And for most of the public that interacted with it, it felt like magic, like actual magic. And even for grizzled data scientists, experienced data scientists, it felt even to them like everything had changed. And frankly, it probably has. For better or worse, maybe both. But everyone in this room knows that even though generative AI is going to garner headlines and the attention of industry and government and academia for the foreseeable future, Gen AI is only one small part of the overall AI landscape. Sure, it's a new tool, for sure. It's going to be a powerful tool, for sure. But there's still enormous value that can be extracted from the other applications of machine learning. So last year on this stage, I spoke about the best practices for increasing model adoption, improving the odds that you can get your model actually into production. Well, today you're going to hear variations on a different theme. And that theme is scaling the impact of your machine learning algorithms through the careful and well-orchestrated integration into your core retail applications. You're going to hear use cases that span e-commerce, core merchandising, end-of-season clearance, and inventory availability. And so I'm going to start along with Meredith, and we're going to talk about a problem that vexes all brick and mortar retailers, which is out of stocks. Now, when giving talks inside a Target and at conferences, it's very typical for us to show pictures of our gorgeous stores, and the shelves are stuffed full with inventory and products, which delights our guests. And that is very typically what we show, kind of pictures like this. And many times our stores do look like this. But at other times, we simply don't have enough inventory to keep the shelves full, or we don't have the right inventory to keep the shelves full, and we don't have enough team member time to go around and research every gap on every shelf. And if we're really being honest with ourselves, we have to admit that sometimes this is actually what our guests see when they shop our stores. Now, every physical retailer, brick and mortar retailer, measures out of stock or on-shelf availability as a key operating metric. But it's usually measured systematically, which means that your inventory systems have to know that the on-hand quantity is zero in order for it to calculate correctly in the metric. But what we've discovered is that when we do physical audits of our stores, and we do those once a year for every single store, when we count every unit of over 100,000 different SKUs in our stores, one of the things that we've discovered is that a significant portion of our out-of-stocks were actually unknown to us, meaning that the system, the inventory system, thought that the on-hand quantity was greater than zero when we didn't actually have the inventory in the store. And so that means that we had to face the hard truth that our out-of-stock metric was probably underreported. So how does this happen? How do you get that kind of drift between the reality on the ground in the store and what the system thinks that you have on hand? Well, every retailer knows that keeping physical track of every unit in the store it's impossible. And shipping and receiving errors, misplacement of items, theft, system glitches, all of those things conspire to screw up on-hand quantities. The term in the industry is called shrink. And so if your system thinks you have 10 soccer balls on the shelf and you have closer to zero, it's not going to send a replenishment. And eventually your sales of soccer balls will go to zero because you're out of stock and your system doesn't know it. Well, fortunately, AI is really well positioned to help solve unknown out-of-stocks and inventory availability. Vision computing to the rescue, right? Shelf-edge cameras that do image streaming, image processing, definitely an acceptable approach. We have a very talented vision computing team at Target, and we've tested it ourselves. We've even gone as far as to integrate it into one of our task management applications for our team members. We know that it actually works. But there is a considerable downside to using shelf-edge cameras to solve your unknown out-of-stock problem. And that's because it's extremely expensive to outfit a store that has over 100,000 square feet of sellable space with enough shelf-edge cameras to be reliable. Not only is it a significant upfront capital investment, but you've got the ongoing operating expense of hardware maintenance as well. So instead, we've decided to try and take a different approach. And so we've been deploying a new capability where we infer inventory inaccuracies from analyzing the underlying data patterns and then systematically correct them. We use an ensemble of AI models, and each one of those models is specifically tuned to identify the patterns that are unique to that particular product category. And then they make predictions of unknown out-of-stocks, and then we pass those inferences to our inventory accounting systems, and then they automatically make adjustments to fix the unknown out-of-stock and therefore trigger replenishment back into our stores. As I mentioned earlier today, one of the themes that you're going to hear about today is increasing the impact of ML through integration into core retail applications. This is going to be a use case where we've done exactly that. Now, anytime you are interfacing into an inventory transaction system for a retailer, that is fraught with risk. That integration has to be well-designed and well-considered. And so I want to pass the mic off to Meredith Jordan, who's going to talk about just how we've designed that integration, and she joins us from Minneapolis, Minnesota.
Thanks, Brad, and hello, everyone. My name is Meredith Jordan, and I'm the Vice President of Product Engineering for our store's capabilities, which include inventory. So, what is the inventory ledger? It was built to record any change in inventory position or disposition for every item at every location at Target. And when you think about the fact that Target has nearly 2,000 stores across the US, that is a lot of inventory to keep track of. We also track inventory for items that have multiple locations, even within a single store. So think of something like batteries, which you might find all over. Before we had the ledger, we simply collected and stored the current state information, but we were unable to easily answer questions of why or how we got to that level. And frankly, we got tired of doing the research when people asked us that question. So, like many great inventions created out of the desire to make life just a little bit easier, the inventory ledger was born. The ledger essentially provides a journal of all inventory changes, things like guest sales, replenishment, put away in the back room, order fulfillment, etc. It paints the full picture of inventory for a given item at a specific store. It's transaction aware, understanding the context in which inventory transactions are being done, and it's able to process transactions out of order, recover from upstream issues, as well as detect and resolve anomalies such as duplicate events. And thankfully, it does allow our users to do the research and answer their own questions on inventory position. The ledger is a highly performant system built to operate at Target scale. At peak loads, we process 360,000 inventory transactions per second. And we serve up as many as 16,000 requests for the current inventory position per second. And we're set up to scale beyond this to meet growing demand. Since this was the first time we're going to be making inventory adjustments based on inferences, we had to build an architecture that could be flexible and resilient, all while protecting the accuracy and performance of the ledger. As the work came together, we realized there were multiple initiatives being tested across Target using different machine learning models, shelf weights, light sensors, and shelf edge cameras. Sometimes it felt like everybody at Target had a new idea or method for solving this problem. We agreed to continue to test and evolve all of these methods, using data to drive decisions on how to proceed and develop an architecture that could support this type of learning and experimentation. Let's take a high-level view of the underlying architecture. As is typical at Target, this is an event-driven, stateless polyglot architecture. We listen to inventory transactions events, we write them to the ledger, we update the overall inventory position for every item at every location across Target, and we respond to requests for the current inventory position, as well as historical context of how we arrived at that position, all in real time. A system at this scale requires some cutting-edge engineering. We have 20 instances of RocksDBs that compute our inventory state in real time. We even had to develop a custom sharding scheme to partition the traffic across our Mongo instances because the native sharding scheme didn't work at our scale. Importantly, for this effort, we needed the architecture to be able to react to inferences from a variety of sources while insulating and protecting from an unpredictable result that could have been possible in these early experiments. We also needed to accommodate the batchy nature of updates coming from these inferences. To conserve battery life, sensors and cameras sent us corrections just once a day. Those inferences flowed through the event processing and action correlation pipeline. This enabled us to test any sensor that could be deployed to the store. ML models also sent us corrections once a day. We did not want to do interventions for the same item at the same store too frequently, as we wanted to see how the intervention assisted in correction before taking any additional action. At first, all the inferences triggered manual tasks for a store team member to verify and correct the inventory. Humans were able to check that the suggested changes were correct and ensured we weren't further eroding inventory accuracy. Because there were multiple tests being done, we needed to build a solution that would allow for all of these tests to be run in parallel and give us unbiased results. And those 2 points were very critical for us, running tests in parallel with unbiased results. We had a lot of competing signal types with lots of pride of ownership across the team. To accomplish this, we worked with a separate team outside of each of our areas to help us define and perform strategy agnostic measurements. These measurements were performed repeatedly, comparing our inventory accuracy before and after. We used that data to make decisions on how to proceed, and we quickly realized that continuous measurement was going to be an ongoing need as the models evolved. As we gained confidence in our signal types, we learned we needed a way to systematically decide which method was the best one for the correction. So we developed an arbitration engine to process the correction suggestions from the multiple signal types. Only one of those recommendations for an item wins, and that recommendation is then passed along for correction. As the volume of these correction suggestions grew, human intervention could just not operationally scale. So we moved to automated corrections, building a systematic way to act on the winning suggestion from the arbitration engine. We learned that having a team defining and performing measurements that was separate from the teams developing the solutions allowed for a discrete and unbiased focus on measurement, enabling easier decision-making. Our architecture has effectively decoupled inventory systems from the methods of detecting inaccuracies, allowing us to test new methods in parallel, as well as adopt and coexist with an ensemble of algorithms, each specializing in a specific set of products. Having a collection of algorithms is proving to be critical given the large variety of products that we sell at our stores. Ultimately, we did eliminate sensors and cameras as a mechanism for detection. While they were effective, they proved to be costly and difficult to maintain at our scale. Inventory corrections made by the models have resulted in substantial sales lift for the products that otherwise would not have been available for guests to purchase, and the models continue to learn and improve. Back to you, Brad, for a deeper dive on the models that we are using.
That is the real Meredith Jordan and not a generative AI version of Meredith Jordan. That's your first Gen AI joke of the day. I suspect there'll be more. So how do the models actually work? To find unknown out-of-stocks and correct them, we need to be able to find patterns in the underlying data. That's our item data, that's our replenishment data, it's our sales data, and it's our inventory ledger. However, these patterns can be really complex, and they can actually be as complex as our assortment times our operations. And when we do find patterns, not always do the patterns transfer to other product categories. So finding a pattern that's predictive of an unknown out of stock in food and beverage may not work in slow-moving items like home decor or apparel. But ML algorithms are designed specifically to find solutions that do generalize across the assortment, finding complex patterns in real time within our high-volume, multidimensional data sets. Our algorithms have been trained on millions of examples of unknown out-of-stocks that have occurred in our past, and we've extracted thousands of what you might call simple pattern detectors, with each one defining a unique condition that predicts an unknown out-of-stock. Now, one of these pattern detectors on its own is not accurate enough. But ML supercharges this by optimally combining thousands of these detectors and then finding patterns among the pattern detectors. So when our algorithm does its daily inspection of our items and all of the inventory transactions, if enough of those pattern detectors ignite, then with reasonably high confidence, we can conclude that we have an unknown out of stock. We integrate with the inventory ledger, set the on-hand quantity to 0, which then triggers replenishment and fixes the unknown out of stock. And by validating, as Meredith mentioned, the accuracy of these algorithms in our stores, we've been able to measure the power and the precision firsthand, which gives us the confidence to then deploy the algorithms across almost all of our product categories in almost all of our stores. With plenty of variety in detection signals, the ensemble approach allows us to develop a comprehensive probability of any given item being out of stock. When the probability crosses a certain threshold, which is configurable, by the way, then we automatically intervene to update our systems. Through the use of an ensemble of models, plus the carefully designed integration into our inventory ledger, we know that we're making an impact on our unknown out-of-stocks. We know that we have fuller shelves as a result, and we know that we're delighting our guests, which, as we all know, is the whole reason that we're here in the first place. Thank you very much for your time and attention.